One of the places where conservation of momentum is really handy is in collisions. So here we have mass 1 and mass 2, and we're going to run them into each other. This one's going to have an initial velocity of 0. So it's going to be at rest. Everything's going to be fine. This one's going to have an initial velocity. This is mass 2, has an initial velocity of 0. Mass 1 is going to have an initial velocity of 1.2 meters per second. I've been practicing. So it's going to be moving in that direction. Wait, which direction? I'm constrained. I have 2 directions to move. I can move this way or this way. So I'm going to set up, and I'm going to call this way positive. So let's do that. That's nice and pretty. That way is positive. So now, when I move in this direction, they're going to run into each other and hit. And let's find out what happens. What do I have to do? I've been practicing. Yay, there we go. Let's try that again. Yay. What? Something happened. This one started to move. It got an impulse on it. However, when I look at the system, I know that impulses change momentum. So what kind of, well, there's got to be external impulses. Because remember, impulses are force, right? Force times delta t, and external forces cause changes in momentum. Well, what kind of external forces do I have? I have friction. I'm just going to call this frictionless. It's a little channel. Doesn't have a whole lot of. Once you get it moving, it stays moving for a little while. What about gravity? Well, and the normal force. Well, of the channel. As we look at the free body diagram on this thing, I have the normal force going up, and I have the force of gravity pulling down, but I'm moving side to side. So what does that mean? They're at 90 degrees to what I'm doing, and they cancel each other out. So they disappear in a whiff of mutual annihilation, and so then now I can assume the external forces add up to 0. So now I end up with 0 equals delta P. So P initial equals P final. My initial momentum of the system is mass 1, velocity 1 in the initial direction, plus mass, oh dang, not again. All right. Mass 2, velocity 2 in the direction. That's got to equal mass 1, velocity 1 final, plus mass 2, velocity 2 final. Well, let's see what I got. I got mass 1. Where did I write these things? Mass 1 is 5.4 grams. I got that earlier. Mass 2 is 23 grams. I too got that earlier. So mass 1 is 5.4 grams times my initial speed of 1.2 meters per second plus mass 2, which is 23. But my velocity 2 is 0. Yeah. Mass 1 is 5.4 times the velocity 1 final plus 23 velocity 2 final. One equation and one unknown. I need some more information. I need to know the type of collision. There are 2 types of collisions. The first type is known as an elastic collision. Now you may think about it as in terms of a bouncy ball of things bouncing up and down. There it goes. I'm going to make it. Oh man, almost made it in. So an elastic collision bounces, but we're going to be a little bit more technical. An elastic collision is when kinetic energy is conserved. What does that mean? The change in kinetic energy is 0. The kinetic energy that I started out with has to be the kinetic energy I end up with. That's my definition of elastic. If this condition does not exist, it's not an elastic collision. Well, what if it's not an elastic? What's it called? Well, it's called an inelastic collision. And so by definition, it's when delta Ke doesn't equal 0. So what? What kind of collision was this? Well, the only time you really have elastic collisions is between atoms. But I can cheat it pretty well here. So I can then say it's close enough to an elastic collision. However, So, but what does that mean? All collisions are inelastic unless told otherwise. So you either need some more information, or you need some more information. Where do you get it? I tell you one of the final velocities, or we talk about it being an elastic collision, where the kinetic energy equals 0. Well, I think this one's an elastic collision, partly because it then allows me to keep talking. So that means the change in kinetic energy equals 0. That means the kinetic energy initial equals the kinetic energy final. 1/2 mass 1 velocity 1 initial squared plus 1/2 m2 velocity 2 initial squared equals 1/2 m2 velocity final. Velocity 2 final squared equals plus 1/2 m. Oh, I shouldn't have made that 2. Mass 1, velocity 1, mass 2, velocity 2 final squared. This is a lot of bookkeeping. However, the 2's go away. That's kind of nice. And then I'm going to change colors because my fingers hurt. Mass 1 is 5.4. My velocity 1 is, oh shoot, what's my velocity 1? 1.2 meters squared plus mass 2, which is 23 times my, oh, that's nice. At least that goes away. Mass 1 is 5.4 times velocity 1 final squared plus 23 velocity 2 final squared. There's my second velocity. I now have 2 equations and 2 unknowns. I have my initial equation here from the momentum, and now I have my second equation for my kinetic energy. Now we can solve. I think you can solve it yourself. See you tomorrow.